All right, so welcome back everybody. Last time, just to refresh your memory, we talked about temperature being a property of a system, and we sort of explored the concept of temperature. And so today I want to talk about another system property that's closely related to temperature, and that is pressure. So, in talking about pressure, the first thing to realize is this is a state property. So if you remember back, I believe 2 lectures ago, we were drawing these state diagrams where we have property A and property B, and we can plot the state of our system as a point, measuring how much of each property we have. And pressure is one such property, just like volume, just like temperature. We can also talk about pressure, and so that's what we're going to be doing a lot of this course. So that's why pressure is important, and we need to discuss it. It's important for studying systems. Now, when we motivated temperature, we started by looking at individual tiny particles down at the molecular level, if you remember that. We drew a system. So here I'm going to try and draw like a box. So this box is our system, and we said, okay, let's say that it's filled with some fluid. So there's a bunch of little particles of fluid around inside this box, and then we looked at how it's different characteristics of their wiggling that we talked about more specifically, and that's temperature. Well, for pressure, we're going to kind of start the same way. So here's my box, and here's my little particles. And how, from this picture, do we come up with the notion of pressure? So what I want to do is I want to zoom in on this system. Zoom in right down to the level where we're looking at the molecular level, all right? And so what I want to then do is look at a little patch of the wall of this container. Okay, so I drew it big so you can see it, but this patch is going to be, I'll draw a blown up version of it here. So here's a patch, a little section of the wall of that container. And since we're so zoomed in, we can see what the molecules are doing. And what we'll see if we watch this patch is that over time, we'll notice the molecules, see, remember, the molecules are all swimming around. They all have kinetic energy. They're moving. Okay, I'm just going to draw a few squiggles. They're moving around in this fluid. And if we watch this long enough, what we see is that the molecules are going to come, bump into this, and shoot off. Okay? So they might come from here, bump. They're going to hit this little patch of area in the sidewall of our container. And since all these molecules that are hitting, they come in with some energy, they leave with some other energy in a different direction. And so what they're doing is imparting a force into this little patch of area on the side of our container. And from a molecular level, from a microscopic standpoint, this is what pressure is, all right? So I'm going to write out the definition of pressure down here that's in our textbook, which is normal force per unit area, okay? So what do I mean by normal force? Well, that just means that it's the component of force that's in the perpendicular direction to the area. So you could come in with some angle, and all we're saying with normal force, we may explore this concept later a little bit more in depth, but the word normal means that if you come in with an angle, we don't care about all of the force you've got. We only care about the component of that force that's perpendicular, all right? So in this picture, it would be the component that's coming in or out of the board. If you come in sideways, if my surface is here, and you come in just like this, you're not going to impart any force. If you bump into the wall ever lightly, right, that little bump, that force is in the perpendicular direction. But if you just slide past the wall, you could be touching it, but sliding past it, you're not imparting any force on it, okay? So it's the hitting motion that we care about, that perpendicular force hitting into the wall. And then per unit area, that just means that we look at this little patch and we count up how many times did the particles bump into this little area. Now, you remember in the temperature lecture, I talked about how temperature and pressure were both closely related to energy. And we explained for temperature why that's the case. Well, with pressure, you can kind of get an intuition for that as well. You can think of these particles being really energetic. They're really riled up and they have a lot of energy. Well then, in a certain amount of area, you're going to have a lot of particles bumping into that wall. That force on that little section of wall is going to be high. Whereas if the particles are low energy, and they're just sort of sluggishly moving around, then there's not going to be as many bumping into that little section of wall, and so the pressure is going to go down. So there's an intuitive sense in which pressure is related to energy, and like we talked about before, it's actually just off by a simple factor. So it's very similar to that concept. Now, with this definition, normal force per unit area, we write it this way. So here's the formula for pressure. Force over area. Now the understanding is that this is force normal. I could put a little n for normal if I want, but that's probably all we're going to talk about is normal force here in this lecture, so I'll just leave it as that. And so what would help us understand sort of why this would be the formula? And I want to give you a couple examples to see if this lines up with your intuition. So what am I saying? Why, like for example, why couldn't we multiply force times area? Why isn't that pressure? Why is it force on top and area on the bottom? Well, the force being on top is pretty intuitive. As the force goes up, the pressure is going to go up. We saw that from our example of this little, our definition of this little section of wall. Now the area being on the bottom, think about if we took that same section of wall and we made it bigger. Well, if we make the area bigger, then those particles are going to be bumping into the area less, right? Because the area itself has grown, but the particles haven't. And so the pressure is going to go down. So making the area larger decreases the pressure, and making the area smaller increases the pressure. In mathematical terms, we would say that these are inversely proportional. They have an inverse relationship. And so that explains why, when we're dealing with the formula for pressure, area is in the denominator, it's in the bottom, okay? A couple examples in real life where we see this are, think of a snowshoe. People wear snowshoes because without them, if you only have the area of your foot, that is too little amount of area that you're imparting too much pressure. Think about it, area is smaller, so pressure goes up. But when they take that foot area and they expand it out to the size of a snowshoe, they're increasing the area, which lowers the pressure. So you're actually putting less pressure on the snow, and that's why a snowshoe allows you to walk. The example the other way would be, think of a kitchen knife, like you're slicing a tomato. You want to lower, or you want to increase the pressure on that area. That's what allows you to make the cut. You want that concentrated section of your tomato or whatever to have a high pressure. And so what they do is they make the knives razor thin. The thinner you can make that knife edge, the lower the area of that knife edge will be. And so when you cut into it, the higher the pressure you're going to impart to that tomato or whatever you're cutting, okay? So these are some real world examples to sort of derive for us this formula, all right? So let's talk about the units that we're going to use for this formula. If you remember, force is measured in the unit of a Newton, okay? This is N for Newton, and that's something that you guys probably will have seen in previous physics courses. And then we've talked about the units for area in base SI units, and those are meters squared. So newtons per meter squared. Now remember that Newton itself is a nickname. Newton can be derived back to our expression in terms of the 7 base SI units. It's just a combination of distance, mass, and time measurements, all right? But we're using the nickname Newton, and that's what we are familiar with for force. Just like This force unit gets nicknamed Newton. There's also a nickname for the entire unit. So this whole thing is nicknamed the Pascal. And the symbol for that is capital P lowercase a, all right? So the SI, base unit of pressure, is the Pascal. But as we're going to see, there are a lot of other units. So the first thing that I want to do is just draw a section of the metric prefix chart. So I'm going to start here at the bottom with, or I'll start up here. So we have 1 Pascal, and then we get 10, 100, 1,000, and remember that 1,000 makes a kilopascal. So the K means 1,000, and this is a unit that's used quite often for pressure. And it's because the Pascal itself is so small that in real world applications, oftentimes it's just way too small to use. And so on the day-to-day, people would rather talk about kilopascals. It's just a more reasonable unit to use. But then you remember, if we keep going on this chart, we have 10,000, 100,000, and then finally, I'll stop here with 1,000,000. Remember, 1,000,000 was mega. So if you have 1,000,000 pascals, you have 1 megapascal, and this is a unit sometimes used. But actually, on this chart, given only in the units of pressure, they do assign a special name to this 10 to the 5th power. So it's 100,000 pascals. It's a 1 with 5 zeros behind it. And when we're talking about pressure, it gets the name of a bar. Okay? So a bar is 100,000 pascals. Okay? And this is only, again, I'll reiterate, this is only for pressure. We just insert this special thing, and you'll see why in just a second. So this is one special unit. It is a bar, which is 10 to the 5th pascals. That's how it's defined. There are other special units that we use. For example, there's the atmosphere. Now we're going to talk about this in a minute. But remember that all fluids have pressure to them. So right now, I am actually swimming in a fluid, and it's called air. We kind of know that air is made up of molecules. There's oxygen, nitrogen, things like that in the air. And since I'm moving through it, I'm interacting with it, and it has a pressure associated with it. And so people decided historically to measure the pressure of the atmosphere, and they got the pressure of the atmosphere to be about 1.013 bars. Okay, we just defined what a bar is. And this is actually the reason why we define a bar as that weird 10 to the 5th. It gets its own name because it's so close to the atmospheric pressure. And they just said, all right, let's define a new unit, which is 1 atmosphere, written ATM. Okay, so you'll see that a bar and an atmosphere are really close. This is almost the same, but it's off by just a little bit. So here's the conversion factor that we're going to be using. There's a really, really important thing that I don't want you to get confused about regarding the atmosphere as a unit. The real atmosphere around me right now fluctuates, and it fluctuates based on weather changes and based on altitude. So as I go higher and higher and higher, the pressure gets lower, and depending on what's happening with the weather, the pressure could go up or down, all right? And so here's how I will phrase this, and I hope this makes sense. The atmosphere around me is not always at 1 atmosphere of pressure. The unit of atmosphere, used as a measuring unit, is defined to be the atmosphere around me at a very specific height and a very specific set of weather conditions. Depending on where I go on Earth or how things change, the atmosphere around me might fluctuate a little bit. It might go up and down, all right? It's not always exactly at 1 atmosphere, all right? So that's a really important distinction. This atmosphere is used as the measuring unit, not as a casual term, oh, 1 atmosphere of pressure, all right? It's a very specific unit. So now, this is still in metric. What you guys probably have all heard of is the imperial unit for pressure, which is the pound per square inch. And we get that because we can come back to here, and here we used newtons and meters squared, which are base units in the SI system. Well, the newton, again, was a nickname, but these are SI units, or metric units. We could also, instead of newtons for force, use pounds force. And I do write the little F because in the imperial system they were so lazy that they named their mass and their force unit the same thing. So pound force, and then the unit of area on the bottom that is commonly used is inches squared. So this is just the same formula, force over area, expressed in the imperial units. And of course, we know that this is 1 PSI, or pounds per square inch, okay? The conversion factor between the PSI and the atmosphere is that 1 PSI is 14.696 atmospheres. So, okay, so if I'm at 1 atmosphere, I am at about 14.5 PSIs, and some of you may have known that. So that's a fun fact. That's about atmospheric pressure. The air that I'm swimming in right now is about that many PSIs. All right, so you guys probably would also remember this from like a tire. We're going to talk about a tire as an example later of the next thing that I want to discuss. All right, so I'm going to raise this board. And now here, I'm going to draw something that's probably very familiar to you. This is another scale. Now we saw scales like this when we were talking about temperature, okay? And we're going to draw the same looking scale, but we're going to use the scale to measure pressure. All right, so you remember that for temperature, there was an absolute 0 point. We couldn't quite get to it, but we could mark it on our scale. So this is going to be absolute 0 down here. Now for pressure, absolute 0 is a real thing. Remember the definition of pressure. So pressure is just force per unit area, and if there is no force, then there's no pressure. So on a pressure scale, there may be situations where absolute 0 is a real thing. So we can go down and we get to 0 at the end. As we come up, we start measuring, and we could say we're measuring in units of pascals or atmospheres or anything. And so I'm going to mark on this graph, maybe, let's say 1 atmosphere. All right, this is atmospheric conditions, whatever happens to be at the moment. And sometimes this is specifically one unit of atmosphere. Again, remember we talked about that difference. So keep in mind, if the problem is telling you what the atmospheric pressure is, or whether they're assuming that you're just going to use 1 atmosphere. Now, where do we go from here? Maybe I'm dealing with a system like a tire, like I just brought up. And a tire would be somewhere up here. It's pressurized more high pressure than the atmosphere is. So tires, we like to inflate them to maybe 30 PSI or something. So if the atmosphere is at like 14.5, we're going to still come up further and go to 30 PSI. But that 30 PSI is measured relative to the atmosphere. So it means that the total pressure, including the atmospheric and what you've added to the tire, is more like 44.5, okay? And that, I hope that makes sense here in a minute, because if I'm up at a pressure like this, I can measure it 2 ways. I can measure it either from that 0 end, so I can go all the way up here, and this is my number, whatever my pressure is, way up here, and this would be an absolute pressure, or I can decide to measure it from my 1 atmosphere point. And if I do this, it's called a gauge pressure, spelled G-A-G-E. All right? And so when I'm talking about filling my tires to 30 PSI, that 30 is actually only a gauge pressure. That's what I mean about having to add in the atmospheric pressure. So this should look familiar. Remember that when we did temperature, we talked about setting a different 0 point than absolute 0. So we could throw our 0 degrees Celsius anywhere on the scale, and we could measure positive and negative temperatures relative to it. This is essentially the same idea. We have one atmosphere, and now I'm going to measure gauge pressures relative to it. All right? It's like I'm setting a different 0 point. Now, it'll only be that if I specify that it's a gauge pressure. All right? So if you just get a pressure with no other context, it's probably an absolute pressure. But there's going to be a lot of problems and circumstances where you're going to be dealing with gauge pressures, and most likely you'll be told that somewhere in the problem, or it'll be inferred by the information in the problem that what you're dealing with is a gauge pressure. So it's measured relative, not to the absolute 0 point, but relative to the 1 atmosphere point. Okay. Now, I could have a gauge pressure positive, but imagine I was down here and I had my gauge pressure negative. So I'm below the atmospheric point, but I still want to measure the pressure relative to this as my 0 point. In that case, it's still called gauge pressure, but some people call it something else. So I'm just going to reiterate that my gauge pressure could be negative and it could be positive. And sometimes when it's negative, this is called vacuum pressure. All right? So you guys have heard of vacuum pressure, I'm sure. This is all it means. It's a special case of a gauge pressure. Now, you don't have to call negative gauge pressures vacuum pressures. You could just say the gauge pressure is whatever, negative 10 psi or something like this, all right? But it's the word vacuum is just another option. You could just report the absolute value and say it's a vacuum pressure. So I could say it's a gauge pressure of -10, or it's a vacuum pressure of 10. All right? You see how that's the equivalent? The word vacuum just indicates that you're using this negative gauge pressure without having to report it as a negative number. So the formulas to get gauge and vacuum pressures are super simple. You can probably already deduce them, but I'm going to write them down anyway. The pressure gauge is going to be pressure pressure absolute minus pressure atmospheric, because remember, you come up to your absolute pressure, and to find the difference, you have to subtract off the atmosphere. And then the pressure vacuum is the pressure atmospheric minus the pressure gauge. And you can tell that this is right because these are inverses of each other. Remember that vacuum is just a negative gauge pressure? Well, if you just flip these two things around, you gain that minus sign. All right? So here are the formulas for relating gauge pressure to absolute pressure. Okay, so let me partition off another section of the board. Now, there's something important, and I want to go back to the idea that I'm swimming in a fluid right now. So how is the atmosphere actually measured in this fluid called air that I'm in? Well, first we can start with the idea that we remember that it's a force per unit area. So if there's a pressure on me, then where is it coming from? It's coming from the weight of the fluid. So I want to just write this to refresh your memory. Weight is a force. It's not to be mixed up with mass, all right? Mass would just be m, weight is mg. On Earth, we multiply it by the gravitational acceleration constant. And so multiplying by that constant turns it into a force. It's got units of force, and we call it weight. So this fluid that's above me right now is weighing down on me. that's where the pressure comes from. That's where the force comes from to create a pressure on me, all right? And the way we're going to see this is by looking at an example system with a fluid in it. So here I am with a container, and maybe we're looking at the ocean or something like this, but I have a container and it's got some sort of fluid, all right? And in this case, we can think of it as maybe a liquid fluid, but it doesn't really matter. You can think of it as any fluid you want. Now, to define a pressure, we're going to need an area. So I'm going to draw down here a little patch of area, and I'm going to draw its dimensions. We could call it this way x, and this way y. All right, so it's got one side that's x units long, and one side that's y units long. That's what I mean by this. And above this, there is an imaginary column. So I'm going to draw this in. You can imagine this. All of the fluid that's above this area, this fluid is pushing down on it. All right? Not necessarily fluid over here. This particle, that's not contributing, but this, since it's inside that column, it's everything above that that's being pulled down by gravity, weighing down on it. Now, let's try and figure out the volume of this fluid, right? Because if we're going to figure out its weight, that seems like a logical thing to start with. So we need 3 dimensions. The first one is this width, which is y. See that it's the same as this. Then of course we have the distance across, which is x. This column is the same width as the area. That's how the column is defined. And then we've got the height from here up to the surface. And this we can call h. All right, h for the height of the column. So we know that the volume of this, and I'll write it down here, volume of this is x times y times h. It's the volume of that fluid. Now, how much does that fluid weigh? Well, we know that W equals mg, kind of what I wrote up top. So the weight is the mass times gravity. We don't exactly know the mass, but what we can do is we can substitute for it. Remember the density formula? This is, I'm going to write this down here. This is rho. We talked about this already, the letter rho for density. And density is typically just mass over volume, all right? Interesting note, since we're talking about density, you guys have talked, I think in every class that we've met, we've talked about specific volume, which was volume divided by mass. So if you notice, these two things are inverses of each other. The density and the specific volume are just opposites. So if I flip one, if I put one over either one of these, I'm going to get the other, okay? So that's just a little side note. And so what I want to do with this real quick is isolate the mass by multiplying both sides by volume. So what I can do is put a volume on this side, and I've just got mass, okay? I hope this makes sense. And so this is what I'm going to plug in to my formula. So instead of mass, I can put in volume times density. But the density could change depending on what fluid I'm in. That's why I'm leaving it totally symbolic, totally general. This could be the density for any fluid. Now, when I put this in, I want to simplify this by plugging in the volume formula, which is x times y times h. X times y times h times rho times g. So this is as simple as I can make the weight right here. And I hope you see where all these factors came from. All right. Now, remember that for pressure, when I want to compute the pressure, I have to do the force, which in this case is weight, over the area. All right. So for weight, I'm going to plug in what we have, x, y, h, rho, g. And for area, we're talking about this little patch that I've defined down here. Well, what's the area? I just multiply the side lengths, which are x and y. So, if I want to write this in simplest terms, get my final answer, pressure equals, you'll notice the x and y cancel out. okay? And we're left with rho times G times H. And I'm gonna box this as well, because this is gonna turn out to be a very, very fundamentally important equation for us. Pressure equals rho GH. So that means that there are three things contributing to the pressure at any given point. Obviously, what fluid we're in contributes, because that's the density. Depending on the different fluids, we'll have different densities. The acceleration due to gravity. So on Earth, that's generally the same. It just changes a little bit, and that's complicated. But on another planet, it would be very different. Okay, so we have to assume that we're on Earth or know the G of whatever system we're working with. And then H is the depth, or the distance below how far down into this fluid are we. So to specify any given pressure, I really need to know those three pieces of information. If I am on a factory floor and I ask you for a pressure real quick, you have to come up with those three different pieces of information to give me a pressure. And because of this, there is a lazy way to do it. I can eliminate a few pieces of information if we all agree that we're talking about the same thing. So here's what I mean. What if we're in the factory and the factory only makes one thing? We're all dealing with one fluid, okay? So you don't have to tell me every time it's the pressure of this fluid and keep telling it to me over and over. We can assume that we all know the fluid. We could also assume the same thing about gravity. If we're on Earth, and we're all at the same spot on Earth especially, then G is going to be the same for all of us as well. And so I'm going to write up here a shortcut way of conveying information about pressure. We can just do pressure as the depth, all right? So here I've divided out by rho G. I've divided out by the density and the gravity. Now I'm going to write what's required. So I need to know if we all know what fluid and that we're on Earth. Okay, these two important factors. If we can all know this and agree to it, and not have to say it every time because it's not changing at all in the course of our calculations, then we can assume these two pieces of information, and we can just talk about the height. When we do that, when we do this shortcut, we sometimes call this the head, all right? It's like a nickname for talking about pressures, and the nickname is used when we're talking about this simplified version, which is just the height itself, all right? So that's some terminology to know and remember. Now, this story gets a little bit more complicated because here I was doing one fluid that we were down in, all right, under the surface of maybe a liquid, but we have to remember there's going to be air above this, right? There's going to be fluid above this. I can continue up my column, and I have to say, what about all this? What about all this pressure weighing down? Well, do I need to do this same calculation over again? Do I need to calculate out the area and do all this? No, because remember, we've got a nickname for the pressure from the column of air above me, and that is the pressure atmospheric. So if I'm concerned with this entire column, and I'll write it up here, so this is my final answer for the whole column, I first incorporate, so pressure absolute, I first incorporate in the air, which is the pressure atmospheric, and then I add to it the pressure from this depth, which we just determined was rho GH, okay? So this would be the full expression if you're asked to find the absolute pressure, is you take your rho GH and you have to also add in the atmospheric, all right? Now the last thing that I want to talk about relating to this is how does the pressure get affected by the shape of my container? So I've been drawing nice, neat containers, but here I'm going to draw a container that's not so nice and neat, okay? So this is now the container that I'm working with, all right? It's got lots of jagged edges, it's got lots of weird shapes, and let's say that we have some fluid in it. Now, there's a principle that governs this and actually makes it fairly simple, and it's called Pascal's law. And our book sort of phrases it in a weird way, and I'm hoping that I can phrase it to you in a more intuitive way. And the simple idea is that the pressure at any 2 points in this container is going to be the same. Notice that they're connected by the same fluid on top. All right, this fluid fills the whole thing. And so if I specified a point down here and a point down here, these are at the same depth or height above the level of liquid. Those 2 points are connected by this chamber with all the same liquid in it. And Pascal's law is basically saying that the pressure is going to be constant through, because it's all the same fluid, it's all nice, it behaves, it's going to be constant at any depth. And so regardless of the shape of the container that I'm dealing with, as long as I have the same height, as long as these two things are at the same height, they're going to have the same pressure, okay? If I add a little bit of liquid, so let's say that I add a little bit more of my fluid and I raise the fluid level, well, we know that now the height has increased, and so we've raised the pressure. Pascal's law tells us that we are going to raise the pressure at both of those points by the same amount, all right? So there's no scenario in this setup with both of these areas connected and all the same fluid and nice and everything. There's no scenario in which somehow we dump liquid in and this pressure raises, but this one doesn't. And you guys are probably like, I get it. Yeah, it's super intuitive, right? Because the liquid is able to flow. And so there's no way that the liquid is going to stack up over here and not stack up on that side. All right, that's how simple the principle is. But I just wanted to give you the name of it, which is Pascal's law. So the last thing I want to do is I'd like to, and I know we talked about lots of units, but I'd like to add even one more unit to our list of pressure units, because these are units that you're going to encounter and you need to know what they are and where they come from. So remember that I talked about the atmosphere fluctuating, not being exactly one unit of atmosphere. Let's say that on any given day, I want to know, well, what is the exact measurement? Okay, where is the atmosphere where I'm at with the weather conditions I'm in? What's the atmosphere? Well, there was this guy, I think his name was Torricelli, and he came up with an interesting measurement device for measuring the atmospheric pressure. And so I'm going to try and draw it for you, at least a cross-section of it. So here's a cross-section of his measuring device, and he called it a barometer. So barometers are fairly old technology, but they're still around today. Like my house right now has a barometer to measure the pressure. All right, so you guys are familiar with these today, but it is kind of an old piece of equipment. And here's how a barometer works. There's some fluid that is filling this bowl at the bottom. Okay, there's some fluid level across here. And historically, what fluid was used was mercury, liquid mercury, because it's liquid at room temperatures, all right? And so this, you can imagine this filled with mercury, but then remember the atmosphere has pressure, and that pressure comes from the weight of the molecules in the air. And so there's a force, a weight from, and I won't say one atmosphere, I don't want to confuse you with the exact unit, but whatever the atmosphere is, those molecules are weighing down and they're pushing down on this mercury, on this liquid in here. That creates a pressure because there's an area and we have a force. And so what that does is pushes this liquid in here. So this lowers, this liquid level lowers because of the pressure from above, and this one rises. So these are lowering, and this is rising. And so you can see how, as the pressure from the atmosphere fluctuates, this level of mercury in this tube right here also fluctuates. And it's in direct correspondence with what the pressure of the atmosphere is. So by scaling this wall of this tube and putting marks or putting a scale on the side of it, you're able to read off what the pressure is. And again, historically, this was marked out in millimeters. So this is a millimeter scale, and this fluid in here was mercury, which the atomic symbol for is Hg, all right? And so from this weird apparatus and the choice of fluid and scale used, there is a new unit that we can define, which is the millimeter of mercury. So I'll write that as a pressure unit, and it's written like this, millimeters of mercury. So it's kind of a weird unit, and it comes from this piece of equipment. And what they actually did is when they measured the atmosphere, they measured it in millimeters of mercury, and they determined it to be 760. So on that, when they decided to measure it under those conditions, that means this column of mercury was 760 millimeters tall. And that's what they measured it at. So that means that the conversion factor, I'm going to pull this board back down, where I had my conversion factors, and I'm going to add, no, lower this a little bit. I'm going to add 760 millimeters of mercury equals 1 atmosphere. So there's a new unit, and this here was PSI, I believe. Okay, so there's a new unit, and this is what defines the atmosphere, so then it gives us the conversion factor. This is also sometimes called a torr, based on Torricelli, the guy who made the thing. So I'll also write torr. Okay, so it's the same thing. A torr is a millimeter of mercury. So I just want you to be aware of that because you'll see this unit popping up. All right, so that's a kind of a brief overview of pressure, what it is. And so next time, we're going to be talking about the changing states of a function. So we're going to come back to, now that we have a good understanding of pressure, what it is, how to measure it, come back to the concept of then plotting pressure on one of these state diagrams. All right, so thank you guys very much. I'll see you next time.